This is the introduction to section 2.3. As we're looking at 2.3, we're going to start talking about biconditionals and definitions. Okay, our objective here is to write biconditionals. We're going to talk about what those are and recognize good definitions. Okay, now a definition is good if it can be written as a biconditional, and we're going to talk about what biconditionals are here in a second. Okay, so a definition is good if it can be written as a biconditional. A biconditional is a single true statement that combines a true conditional and its true converse. You can write a biconditional by joining the two parts of each conditional with the phrase if and only if. So you're going to see this a lot here, if and only if. Okay. The only way that a biconditional can be written is if the conditional and the converse are both true. If they're not both true, then you cannot write it as a biconditional. In other words, remember we wrote the conditional. Remember the converse took the hypothesis and the conclusion and flipped them. Okay, if I can write both of those as true statements, we can write it as a biconditional. Okay, so writing a biconditional. It says here, what is the converse of the following true conditional? If the converse is also true, rewrite the statements as a biconditional. Okay, so here's the conditional statement. If the sum of the measures of two angles is 180 degrees, then the two angles are supplementary. Okay, so what we need to do now is we need to take and find the converse. Okay, well the converse of that reads, if two angles are supplementary, then the sum of the angles is 180 degrees. Is that true? Well, of course it is. If two angles are supplementary, they add up to be 180. So right now, I know that both my converse and my conditional are both true statements. Okay? So this is a true statement, and this is a true statement. Both of these guys are true. So if they're both true statements, I can write it all as one statement. Okay? All as one statement. Okay, and write the words if and only if in the middle. So you'll notice you have if and only if. If you look here at the bottom, the biconditional states two angles are supplementary if and only if the sum of the angles is 180 degrees. So a couple things about this. This part right here, two angles are supplementary. Okay, that is the conclusion or hypothesis. In this case, the conclusion. Okay, this is the hypothesis of the conditional. Okay, so essentially all I'm doing here is taking the conclusion and the hypothesis, and the question is going to be, shouldn't the hypothesis be first? And it could be, absolutely. It doesn't really matter which way you put it because they're both true. So I could say the sum of angles, the angles is 180 degrees if and only if the two angles are supplementary. I could flip that around. That's the exact same thing. Okay, so let's look over here on the right, another one. It says here, what's the converse of the following? If the converse is also true, rewrite it as biconditional. Here's the statement. If two angles have equal measure, then the angles are congruent. Well, the converse is, if the angles are congruent, then they have equal measure. Is that true? Well, yes, it is. If the angles are congruent, they have equal measure. That's true. So, now because they're both true, again, the converse is true, the conditional statement is true, I can write these as a biconditional. And the biconditional that we've written is, two angles have equal measure if and only if they are congruent. Now, on this one, you'll notice that this first part is the hypothesis, and the second part is the conclusion. And that's okay. It doesn't really matter either way because, again, both statements are true. Most of the time, you're going to put hypothesis first, conclusion second. Okay? All right, so we've written biconditional statements now, so this kind of goes through and explains here. It says a biconditional statement combines if P then Q and if Q then P as to P if and only if Q, and that's what that means right here. P if and only if Q. That's what the double arrow means on both directions. Okay. A point is a midpoint if and only if it divides a segment into two congruent segments. Okay. So in this case, this is an example of a biconditional. Okay, now let's take a look here at identifying conditionals in a biconditional. Okay, so now we're going to kind of go backwards. You'll notice that a biconditional is made up of a conditional and its converse. They both have to be true. So what are the two conditional statements that form this biconditional? Okay, so in other words, I want to figure out what's the conditional, what's the converse from this biconditional statement. A ray is an angle bisector if and only if it divides an angle into two congruent angles. Okay, so remember this part right here again, this is the hypothesis, and this is the conclusion. Okay, so that's the important part. So if you can identify hypothesis and conclusion, you can put them into conditionals and converses. So the conditional statement here with the hypothesis says, if a ray is an angle bisector, then it divides an angle into two congruent parts. Okay. Once we find the conditional, we can find the converse. The converse here states that if a ray divides an angle into two congruent angles, then the ray is an angle bisector. Okay. This right here, I should probably cross this out and make this parts because it's the same sentence. It'll be the same thing. Okay. So you can make from a biconditional, you can make two statements, the conditional statement and a converse statement as well. All right, this one here, I want you guys to be able to do on your own. So before you come to class tomorrow, be able to write the converse and the conditional for this statement. Two numbers are reciprocals if and only if their product is 1. Okay, so let's go to the next part here. As you learned in lesson 1-2, terms such as points, lines, and planes are building blocks of geometry. You understand the meanings of these terms intuitively. Then you use them to define such terms such as a segment. A good definition is a statement that can help you identify or classify an object. Good definition has several important components. Okay? Good definition uses clearly understood terms. These terms should be commonly understood or already defined. A good definition is precise. Good definitions avoid such words as large, sort of, and almost. And a good definition is reversible. That means you can write it as write a good definition as a true biconditional. Okay? So, writing a definition as a biconditional. It says here, is this definition of quadrilateral reversible? If yes, write it as a true biconditional. Here's the definition. Okay? A quadrilateral is a polygon with 4 sides. So what I went ahead and did is I broke it down into a conditional statement and a converse statement. So the conditional statement I came up with was, if a polygon is a quadrilateral, then it has 4 sides. Okay, that's true. The converse says if a polygon has 4 sides, then it is a quadrilateral. Well, this is true as well. Both of these are true. So now, because they're both true, I can write it as a biconditional statement, which means that the definition is reversible, which means it's a good definition. Okay? So the biconditional here is a polygon is a quadrilateral if and only if it has 4 sides. Okay? Again, here's the hypothesis. Here's the conclusion. Okay? All right, so what I want you to do is I want you to determine, is this definition of straight angle reversible? I want you to write 3 things. I want you to write the conditional, the converse, and if they're both true, write the biconditional with it as well. Okay, last thing here that we're going to look at is determining if it's a good definition. Which of the following is a good definition? Okay. So, remember, as we're looking for a good definition, we're looking for, is it reversible? Can I do it both ways? Okay. So, letter A says a fish is an animal that swims. Okay. So, if I were to write this as a conditional here, I would say if the animal is a fish, then it swims. Okay. If I flip that, if the animal swims, then it is a fish. Is that true? Is that true? Well, that's not true. This is not reversible. Because you could say, give me 1 Counterexample. Well, a whale is not a fish, and it swims. That's a counterexample. So that's not a good definition. Okay. Let's go letter. Let's take a look at letter D. Okay. What I'm going to have you do is I'm going to want you to do these two by yourself, B and C. But letter D. A penny is a coin worth 1 cent. Okay. All right. So if I were to write this as an if-then statement, if the coin is a penny, then it's worth 1 cent. That's true. If I were to flip that around, if the coin is worth 1 cent, then it is a penny. That's also true. This is, yes, that's a good definition because it is reversible. I can write it as a biconditional. I could say a penny is a coin if and only if it's worth 1 cent. Or the coin is a penny if and only if it's worth 1 cent. Or I could say if the coin is worth 1 cent if and only if it is a penny. Okay. So what I want you to do is I want you to finish up C, B, and C here for me. Figure out and see if those are good definitions, and we'll talk about those in class tomorrow. Okay. All right. This concludes section 2.3. Introduction to section 2.3, your notes. Don't forget to complete your WSQ before you are finished.